Good morning, everyone. I hope you're doing well today. So I want to make a couple of announcements. The first one is regarding our second midterm. I have graded most of them. I still have maybe a dozen. So I will finish that before next week. And you should be able to see your the updated score eventually. So should be at the end of this week before Monday. Also, I noticed that some of you did not submit your work for the where it says to upload your file. So if that was simply a mistake where you meant to submit and you somehow wasn't able to, let me know, and you could send those work to me by your email, okay? Now, if you did not have a chance to upload during your exam. The second update I want to talk about is your grade estimate. You should be able to see a grade estimate right now in your Canvas. I have incorporated your pre-lectures, homework assignments from Achieve, and those scores should all now be viewable under Canvas. So as more assignment is being completed, those more scores will be released and your score will continue to be updated. So overall, at the gradebook, you can see that at the end of those, all of the columns for individual assignments, the overall pre-lectures and bridge questions counts for 10%. The overall homework assignments counts for 20%. Exam 1 and 2 counts for another 20% each. Final 30%. So then you should be able to see a total grade that it's computed for you. The pre-assessment, the diagnostic assessment you did, because I need a score for myself, even though I'm now counting the score for your participation. So even though it's showing as a score, counted as 0% of the grades. So whatever you see right now, let's say if your total grade right now is 80%, if you have already done the pre-assessment, you can assume your final overall score is 81. So simply just add 1 yourself. I couldn't change that's already being a graded assignment to an extra credit. So I would just leave that to you, simply add 1 more point for yourself. The same goes for our post-assessment. After our semester is over, I will compute everything and those will be converted. Simply 2 more points will be added onto whatever you see in Canvas. Are there any questions regarding the grade the grade estimate and also our midterm? Are there any questions? I will be posting exam solutions. I just wanted to wait a little bit until everybody has a chance to give me whatever they need. Any other questions?
Is the final going to be cumulative, or is it just going to be the new stuff after midterm 2?
That's a great question. What is the final going to be? I think it's going to be heavily concentrated on the later chapters because we already spent quite a lot of time on the previous ones. I couldn't say it's not cumulative because you know how it is. In order to answer later on a question in angular momentum, you may have to still use forces. Sometimes you still need to use energies, right? So we could not say, well, you don't need any of those previous chapters. So it is cumulative, but you should see a more focus and emphasis on the later chapters.
Cool.
Thank you for that question. Any other questions?
For the final, will we get a study guide or like a practice review sheet as well?
Yes, so there will also be a review, just like practice game like the other ones. Yeah.
Okay, thank you.
Sure. Any other questions? Okay, all right. So if you do have any more questions later on, feel free to email me and let's continue with our Discussion on rotational motion. 1 second. Okay, let me share this again. It didn't work. Okay, all right. So we talked about torque. We talked about Newton's second law for rotation. The one last thing for rotation we want to discuss is angular momentum. So all the linear cases, we have found an angular analog for linear velocity, linear position, linear acceleration. The force become torque, mass become I, the rotational inertia. So the linear momentum becomes angular momentum. So you can pretty much already guess what the angular momentum look like simply by taking a look at our linear momentum, right? So V, the linear velocity, will now become omega angular velocity, and the mass will become I, rotational inertia. So overall, the angular momentum, we use the letter capital L to represent it. So L is I alpha, I omega. So this is the definition for angular momentum. Now, if you have trouble memorizing this definition, you can always think back, okay, what was the linear case for momentum? And then you can try write it out for the angular analog. So angular momentum, L is I omega. We know that for something that is rotating, sometimes it's a little particle. Sometimes it is a continuous distribution like a disk or a sphere. So we can, when it's a particle-like object that is rotating, then we will have another definition for the angular momentum that we can write it using R cross P. But you can see these two are not really all that different, and I'll show you how they are equivalent. So for example, let's consider a point particle, a little mass that is rotating around the center of axis. This is a rotation. So we're going to use this equation, right? R cross P. So R is pointing from the center of the rotation to where the object is. So that is your R. And P is a linear momentum. So at this point, the linear momentum, if it's rotating counterclockwise, the velocity is tangential to the path. So this is mv. Okay. And if I do R cross P, you can see that at any point along this path, R and P are perpendicular, right? Because at a circle, right, the tangential direction is always perpendicular to the radius direction. So they're always perpendicular, which means sine of the angle between them when you do cross product is sine 90 degrees becomes 1. So it's simply just R times mv. All right. And what is a linear velocity? Linear velocity is angular velocity times radius r, right? So I replace v with omega r. So you can have m r squared and times omega. So what is mr squared? You have a little mass m, and that is rotating with a distance r away from the center of the axis. So mr squared turned out to be the angular rotational inertia for the point particle. So it is I times omega. Okay, so you can see that these two equations are not all that different. It's just when we have a particle traveling, we prefer to use this equation. You have a rigid body, a continuous distribution, you use this equation. Okay, so let's practice that by taking a look at this particular question. So here we have a point particle, an asteroid is heading towards the Earth, aimed right at the center of the Earth. So the velocity of the asteroid is showing as this arrow right here. It has this particular velocity, 10 meters per second, and 10 to the power a million kilograms, and is currently at a million kilometers away. So it's asking for the angular momentum of the asteroid with respect to the center of the Earth. So we're going to use this definition to calculate it. Okay, so this is a point particle. A point particle doesn't have to be small. It's just for whatever we consider, you don't have to think about the shape of the particle. All of the different shapes have the same physics as far as we're concerned. So even though the asteroid may be big, but in terms of its motion toward the Earth, we can simply view it as a point. All right, so I don't think this one we need to discuss. I will simply go ahead and open the poll for you. Whenever you're ready, you can go ahead and put your answer in. I do want you to stop and think about the definition before you start plugging numbers, okay? There is a little bit nuance in it, not just to plug in numbers. So R is a vector, P is a vector. Think about what is your R vector? What is your P vector? And what is the angle between them before you answer the question? Okay, 10 more seconds for us to wrap up. All right, are there any last minute vote? Okay, let me go ahead and close this. We'll take a look together. We're pretty much split between the first three choices, A, B, and C. Okay. All right, so let's think about, before we plug in numbers, let's draw a vector that represent R. Can anybody tell us, how should I draw this vector R?
So R could be drawn from Earth to the asteroid.
Okay.
And, the direction, I would imagine, because Earth is like where we're like heading to, that it would be, the vector arrow is pointing towards the asteroid.
Yes. So
because then it's like more of a circle, and it produces like an angle, if that makes sense.
yes, it does. So it's asking, okay, angular momentum is talking about this rotation relative to where. So we want to say, what is angular momentum with respect to the center of the Earth? So assuming that rotation will be happening relative to the Earth. So you go from the center of the rotation to where the object is, and that is R. So that little radius outward is this r direction. And p is our momentum. So momentum is m times v, simply is the direction of the velocity. And that arrow is already shown to us, right? It's the asteroid's velocity, which is directly toward the Earth. So this one is already given to us. So this is P. So R is here, P is here. What would you get if you do a R cross P here?
I believe you would get 0 because the angle between them, it's negative 180 degrees. So sine of that is 0.
Yes, thank you, Juan and Jacob, for responding. This is 0 because they are in the same direction. The angle between them, if you do the cross product, is 180. So sine of 180 is 0. You can see that there is no angular momentum of the asteroid with respect to the Earth, because relative to the Earth, this point particle simply just isn't rotating. It's not going around Earth, it's coming directly at the Earth's center. So of course it shouldn't have any angular momentum, right? So that's just going back to this definition, is when we are looking at the angular momentum, we have to think about, okay, what does R mean and what does P represent? Let's take a look at another question. So instead of a point particle, now we can look at a continuous distribution, a rigid body. So now we have a spinning wheel. We are pretty familiar with what that looks like. And for a rigid body, we use L is I omega. We use the other equation, right? Okay, so there are 3 identical. They're all rotating at the same velocity, counterclockwise. So omega is upward. So when you add up the total angular momentum of all 3 together is 3I omega. Now let's flip one of the wheels upside down. What will be the new angular momentum of our system? All right, so again, I will open up the poll for you.
Professor, do we take the absolute value before adding them all up or after adding them all up? Or is that something you want us to figure out for the question?
Yeah, that is what you have to figure out for the question. It's asking you the absolute value for the total. So this is a vector, so it's like adding up forces.
Cool, thank you.
About how you add up forces, and this is the same thing. Okay, so we will go for another 10 seconds. All right. Any last minute vote? Let me go ahead and close it. Okay, so this is our results. We're adding, seems like if we were voting for A, right, still 3, then we are adding them up using the magnitude of each of them. So we take the absolute value of each of them and then add them up. But remember, angular momentum is a vector. So we need to do a vector addition instead of adding up like scalars. So if you have forces, let's say if we're adding forces, you have 1 up, 10 newtons, 1 up, 10 newtons, 1 up, 10 newtons, we say, okay, overall 3 newtons upward. But if I flip one of them, 1 up, 10 newtons, another up, 10 newtons, 1 down, 10 newtons, and then I add them, what should I get?
20 newtons.
I've already flipped.
Oh, wait, sorry. Wait. Sorry, 10 newtons.
Yes, very good.
Sorry.
You can see that one of them is a vector, so you can, this 10 and this 10 cancels. You really just have 10 newtons upward. So this is the same. By flipping one of them upside down, you are canceling the angular momentum of the other. So if this is omega, so this one will cancel this one, and the overall will be just one wheel up, rotating upward, right? So the correct answer should be C, I omega. So this is treating them as vectors, so just be very careful. I'm actually surprised there are not more voting for 2 I omega. I thought that would be, you know, treating them as vectors, one of them go away would just be 1 omega less, but we actually more voted for A. At least I'm thinking that we're thinking consistently. If you're thinking this, you're treating L1 plus L2 plus L3, adding them up like scalars, but we're saying they're actually vectors. So you should add them up like this, and that give you I omega. Okay.
I have a question.
Yeah, go ahead.
Why is it not B?
Why is not B, right? Is that the question?
Yeah.
Okay, so it's not B. We can look at the analogy of using the forces. So you have one force pointing up, which is 10 newtons, another force pointing up, which is 10 newtons, and a third force pointing down, which is 10 newtons. So you can see these 3 forces add up to be 10 newtons, but not 20, because this one that's up will cancel the other one that is down. So leaving only 10 newtons. So this
That makes sense.
It's yes. So this one is could be a really good tempting choice, but thinking about that, they are vectors. We should be able to answer that correctly. Very good question. Thank you. So let's continue to talk about, okay, now we have defined angular momentum. What else can we, when we get from this new definition? That is, what does Newton's second law becomes? Well, isn't Newton's second law is just F equals ma? We had talked about a different way to write Newton's second law, right? F equals ma. Previously, we had said you can write A as dv dt and move m together with v, because m is, in this case, we're looking at a constant mass, so it's not a variable. You can just multiply any vector, any variable by a constant. So mv become p, right, dp dt. So this is Newton's, another way to write Newton's second law is F equals dp dt. We have a exact analog here, is force becomes torque, linear momentum P becomes angular momentum L, so torque is equal to dl dt. Okay, and again, if we have trouble remembering this, we can think back what we had in the linear case and find the analog. Now this will give us the conservation of angular momentum, which is yet another conservation laws. We have looked at a lot of conservation laws this semester. Those are important laws of nature. We start with conservation of energy. We did conservation of momentum. Conservation of momentum actually come from this, right? Now, here it will give us conservation of angular momentum. So recall when we have the linear case F equals dp dt, when there is no external forces, or in other words, where there's no net external forces. You may have external forces, but they overall cancel out to be zero. When the net force is zero, then dp dt is zero, right? If this is zero, this is zero, which means something, when you take derivative with respect to time, is zero, meaning that this function does not depend on time. So p does not change as time goes on, meaning that the momentum is a constant. So this is a constant, basically, that's what it's saying. So momentum final is equal to momentum initial. Likewise, we have exact same thing going on for rotation, is when there is no external torques, net torques, then L is constant. The angular momentum is constant. Okay, which means the angular momentum L initial is equal to final. It does not change, it remains a constant value. So this has a lot of applications, a lot of our problems we will coming up to see is using angular momentum to solve them. Let's start with a couple questions that you have already seen on the pre-lecture. So for example, now we have a rotating disk. From the top view is rotating counterclockwise like that. And you toss another block onto the disk. So here you kind of have a system of two objects. One is a disk and one is a block. The system has these two objects. One of them can be treated as a point particle, that's your block, right? And your disk is a rigid body. So you have two of them together. By tossing the block onto the disk, let's say the disk itself has some kind of angular momentum, right? And after you toss it, the block will simply land on the disk and then they rotate together. Do you think that you have changed the angular momentum of that entire system by doing this? Do you think that the final angular momentum remains L? Or would it be bigger than L or smaller than L?
Wouldn't it be bigger than L, because then you have like more mass, which is like more momentum, like moving in the angular direction? I don't know.
That's a good point. Yeah, because you have more mass, now instead of rotating just the disk, now you have to rotate the disk and the block. Does that mean our angular momentum decrease? What do the rest of you think?
Well, it would depend on the, it would depend basically on if it's like an engine or something. Because if it's like an engine, it'll keep it, make sure that it's going at that constant speed. But if it's not, then I think angular angular speed, angular velocity would go down a little bit just because you added mass. But because it says a freely rotating disk, I think that it's not the engine case. I think that's what that means.
Okay, there are a lot of good thoughts. So I want to summarize what came up from that discussion, that the overall mass of the system increased from the disk to the disk block system. So mass increased. And Juan just pointed out, depending on if it has an engine. Well, there is an engine here. Because if we do have an engine, that counts towards an external force, external torque. And of course, you can make it rotate however you want. So assuming we don't have that external torque, it's just the disk, you believe that they will slow down a little bit. Very good. Those are really good thoughts. Let's see some more thoughts coming through the chat. I was thinking that similar to elastic collision, the angular velocity would go down with the increased mass. Very good. That's a great point. I agree. The whole thing will probably slow down a little bit. Another thought said equal cause its sine zero. Okay. So you're saying we should choose L because the angle between R and P for the block is 0. All right, those are really great thoughts. So I'm going to walk you through with all that train of thought. Let's think about this together. So you're right that when you have more mass now to rotate, your omega should drop. Okay, so as m increase, you can think about that's equivalent of saying the rotational inertia increase, right? Because rotational inertia is the disk, 1/2 mr squared of the disk plus the little r squared for the block. So now you have an extra object, so I increase, omega decrease. Okay, so but we are asking about the overall angular momentum. So we're not asking angular speed. So it is possible, or could it be possible, as I increase, omega decrease, the overall L still remain the same, which will lead us to choose B. So now let's think about, okay, well, we don't know exactly how I will increase and L will decrease, so didn't really go anywhere with the L. But let's think about the angular momentum of these two systems separately. The disk has its own angular momentum. It's rotating. Now you added a block. So we just want to see, well, by adding the block, are you adding anything extra? Because the disk already had L, right? If the block gives it some extra angular momentum, then the overall eventually should increase or decrease, depending on which direction that added momentum is. But you can see that, does the block carry any angular momentum to the picture, the way that it was thrown like this?
I don't think so, because the angle it makes, looking at the top view, it's like pointing straight towards the radius. So that means the angle is going to not matter, because sine of that angle will be 0.
Yes, this is just like the asteroid coming directly toward the center of the Earth situation. The block actually does not carry any angular momentum as it comes in. So imagine if your disk were originally at rest, by tossing the block on it, it's not going to make the disk rotate at all. It's not going to give the disk any torque. So if the block does not give you any extra angular momentum, so the whole system should still have the same angular momentum, which is L afterwards. So equal to L is correct. Very good. Everybody contribute great thoughts into this.
Professor.
Yes.
So if you're looking at the top view and you toss the angle with an incline towards the counterclockwise direction, then that would add angular velocity, right?
Yes. And in fact, that's tossing it at an angle is this next question we're looking at. So now we said, okay, tossing toward the center doesn't work. Let's toss it at an angle. So it's like this, maybe different from what you had in mind. So if you toss it like this, and the disk still had L to begin with, after you toss it, the whole system should have more than L, equal to L, or less than L. What do you think? Feel free to respond through the chat or talk about it.
So since it's the same freely rotating thing, now when we throw the block, it kind of it's working against the rotation, because like the rotation is kind of going this way, but the block's going that way. So it is decreasing it.
Okay.
I would imagine. And then also the block does add its own mass. So I goes up a little. I mean, sorry, in this context of like, you know, like last time we were talking about how because of the angle it was thrown out, I would go up and W would go down. In this case, I think we don't really have to look at that too much because of the initial direction it was thrown in.
Yes, very good. You can see that this is an attempt to make the whole thing by rotating the opposite way. So it will bring the block bringing a angular momentum that is in the opposite direction to what the disk had to begin with. So if you add angular momentum together as vectors, they will cancel out part of that, right? So overall, the final angular momentum should be less than L. Very good. So you can see how angular momentum, we can just see, okay, which way it is making it to rotate. So right away, we can see, oh, this is causing a clockwise rotation. You could also do the R cross P for the block. Okay, so since my momentum is coming at an angle, not only is hitting it to the left, left down to the right, is also hitting it downward. But the downward one doesn't cause any angular momentum. So I'm going to use my P to be simply in this direction. This is my P, which is equal to mv. There is still a component directly down into the disk, but that one I don't need to worry about that component. And my R is this. I can do R cross P. And again, when you have two vectors that is not overlapping, which is make it harder to rotate, feel free to move them parallelly so it's easier for you to do your right hand. So in this case, I could move my R downward a little. I'm just gonna move my R a little parallelly. So I'm gonna put my R here. And you can see when you do R cross P, right hand rule, R, 4 fingers curling toward P is giving you a downward cross product that's downward. So downward is a clockwise rotation. The original rotation is counterclockwise. And so that they cancel part of that, which will make the entire system have a smaller L eventually. You can, one important thing you can already notice that the system's angular momentum L of the block plus disk is a constant before it landed and after it landed, okay? So this is coming from torque equals dl dt, we just derived earlier. Torque is 0, so L is a constant. There is no external torque acting on the block and disk system. Like Juan said, there's no engine, there's nothing to spinning them up, and we are not considering the friction or air resistance to slow them down. So angular momentum remains a constant. The friction between the block and the disk is an internal force. So that's not an external force, and therefore we have no total torque on the system. But you had all very good insights that when you have more mass to rotate, even though your L remain a constant, L is a constant, but L is I omega. So if I increase, omega should decrease in order for that entire L to remain a constant. So in fact, we use that a lot to answer angular momentum questions. So recall when momentum conservation, we say when momentum is a constant, right? M initial, V initial is equal to M final, V final. For conservation of angular momentum is the same. So I initial, omega initial is equal to I final, omega final. So if I change, omega will also change, but the I omega together remain a constant. There are a lot of applications in this. We'll look at the first demo. It's called a spinning student demo, where a person stands or sits on a spinning platform. They hold some weights. They could either extend their arms or hold their arm toward the center. So by doing this, think about how they have shifted their weights and how did that impact their I, rotational inertia. It's still the same mass, but they have changed the distribution of the mass, more out toward the outside or more toward the center. So as a result, they will spin faster or slower. So let's take a look at that demo together.
So let's say.
Oops.
I have a couple.
Okay, so there's a lot of intro. We don't have to look at intro. I'm just gonna hit from the middle when they start performing, okay?
Okay. You can see my tie flying up. So ice skaters use this principle. They start off in going to their triple toe loop with their arms far apart or away from their bodies. Then they bring their arms in close and they're
Sorry, I don't know why it freeze. Let me share the screen again, but I hope that you got a chance to see what was important earlier, that he had his arms extended out at first and then bring them in toward the center. And what did you see? Did you see that?
The act
one more
bodies,
one more time.
Bodies, then to their triple.
Right.
You can see my tie flying up.
Okay, so as you bring your dumbbell closer to the body, to the center of the body, the person spinning faster, right? As we observe. Anybody would be able to explain that phenomenon using conservation of angular momentum? Can we use I omega I is equal to IF omega F to explain it?
So at the very beginning, I'd like to just talk about the two I's real quick. In I1, the center of mass is the same as in I2, but the mass is farther apart. So that means that our I initial or I1 is going to be greater, right? Okay. So that whatever W is or WI or W1 is doesn't really matter right now. But since they have to be equal, since I2's I is lower than, or IF is lower than II, it has to be W2 to balance out both sides, therefore has to be greater than W1. So that's how they start spinning faster.
Very good. The initial rotational inertia is bigger than the final rotational inertia. That is because part of the mass, for this particular mass, the rotational inertia is mr squared. That's how we calculate, right? So the mass initially has a longer distance away from the center, but when you bring it to the center, they have a much shorter distance or zero distance from the center. So that's why I1 is bigger. If I and omega multiply to be a constant, then omega 1 has to be less than omega 2, right? So as omega, when I decrease, then omega will increase as a consequence of conservation of angular momentum. Excellent, very good. So this is being used a lot. You've probably already seen this. I'm sure all of you have seen this and used in figure skating, but we can take a look at that. Okay, so you can see by bringing the arms inward, the figure skater is able to rotate much faster as taking advantage of conservation of angular momentum. Now, in that case, because they're on ice, so the external torque can be negligible, at least for a short amount of time. Then the angular momentum omega remain constant. As I decrease, by bring your arm in, omega increase. And in fact, it's very hard to do. I gotta do a lot of practice to be able to do this. So if you were ever stepping on a rotating platform, probably see some of that at some of the parks. You can start out rotating, but if you bring your legs in, you're gonna go so much faster. So don't over project the speed, because as you bring your arms in or legs in, you're gonna go so much faster, just so that you can anticipate that, be a little more careful. All right. So for the next one, for the next couple questions, I want to show another demo first, which is very similar to the questions we are going to answer, but not exactly the same. So there's a lot of, okay, on the spinning platform, what we saw that is bring your arms in and out. Now, instead of doing that, this demo is by holding a spinning wheel, and you can do something to that wheel that you're holding, and something will happen. So let's take a look at that. We're only going to look at the very beginning of the demo. We're not going to watch the whole thing.
A stool, which is free to rotate around a vertical axis through the center of the stool. There is no net external torque acting on the stool and me system, so angular momentum of the system is conserved. Initial momentum.
So what is a system? The system is a person plus the stool together. They say the angular momentum of that person plus stool together is conserved. So it was 0 to begin with, and it should be 0 throughout.
System is 0, so as much as I wave my arms and legs around, I cannot cause the system to rotate because the angular momentum of the system will stay 0. Flipping to it. The spin has an angular momentum.
Okay,
if I am holding a spinning wheel, the wheel has an angular momentum, and if I rotate.
So be very careful. Right now you can see he's sitting on a stool, but he is holding a wheel. The wheel is already spinning. So most likely someone have already make the wheel spin and pass it on to him. Okay, so that's how it worked.
Spinning wheel by applying a torque to it, the spinning wheel will apply an equal but opposite torque back on me, which will cause me to rotate. Now realize, angular momentum of the system is still conserved because the two torques, which are equal and opposite, will cancel one another out and result in a net torque on the system of 0. In other words, both of these two torques, the torque I apply to the wheel and the equal but opposite torque the wheel applies on me, are internal to the person, chair, and wheel system. Now let's.
Okay, so they're talking about the internal torques, but let's not worry about it because it's a whole system. But what's interesting was he was not spinning. He was simply holding a wheel that was spinning. By flipping the wheel upside down, he and the stool is able to rotate. So that can be explained using conservation of angular momentum. So we are going to look at a couple questions that's very similar to that, but not exactly the same. Let's start with the first one. I get on a rotating platform initially at rest, and I start spinning a wheel. So this is different from what he did. He already hold a spinning wheel and he flipped it upside down, but we are holding a wheel that was eventually not rotating. Either of me or the wheel are rotating, and you start spinning the wheel. Let's say you spin the wheel clockwise, and what will happen to you and the platform? Okay, so I'm going to go ahead and open our vote, and you can put in your thought. All right. Let's take a look at this together. Sorry, we're running out of time, so let's just take a look at this question together. We're kind of pretty much split between these different answers. So let's consider the person, the platform, and the wheel that it's holding as a whole system. As I said, initially everything is at rest. So the total angular momentum of the entire system is 0. So if you start rotating the wheel and give it a clockwise rotation, which corresponding to a downward angular momentum, what will happen to the angular momentum of the platform and the person? What do you think?
I think that the angular momentum would have to be positive and the same magnitude as whatever the downward momentum was. I mean, the negative z.
If this is -10, there's got to be +10 in order for them to still add up to be 0. Remain constant, right? Very good. So in order for momentum to be conserved, this has to be start rotating counterclockwise with the same entire M is still the same as the wheel. So yes, you will start, you and the platform will start rotating counterclockwise. The wheel is rotating clockwise. So this is very similar to a conservation of momentum where you can have a bomb where initially at rest, you can throw one piece to the right and the other piece will be flying out backwards, but the total momentum still is 0. Here is the total angular momentum still remains 0. All right, so that's all we will talk about today.
I have a question.
Yes, go ahead.
So this is like assuming that we when we first sat down on the platform and started spinning the wheel, because it says and start spinning, so we started spinning the wheel, right?
Yes.
So, but what would happen if like I was just sitting there and let's say you start spinning the wheel and then give it to me? Because wouldn't the wheel be an external force, external angular momentum then?
The wheel was simply just rotating. It's not going to make you rotate. If I simply hand it to you, you are still 0 and I hand you to an extra 10. So initially you just have an extra 10.
Okay.
But if the wheel starts, you flip the wheel upside down to -10, and then you will have to become 20 in order to still add up to be 10. This is what we see in the video.
Okay.
Yeah, very good.
And so then if, so you know how we were talking about the flipping it over? If he doesn't flip it, so like let's say I start spinning it and I don't flip it over, but it just starts spinning, would I then also spin?
Yeah, if the wheel handed over to you, you can see that it's handed over to you, parallel to you, it's not going to cause any rotation.
No, I mean if I start spinning it, but then don't flip it.
Oh, yes. So then you will just continue to rotate counterclockwise until air drag slow you down.
Okay, cool.
Thank you so much. And I'll see you guys next week. If you have anything regarding the midterm, please contact me. And if anything you wanted to see with your grade estimate, also let me know. Bye, everyone. Have a good weekend.
See you later.
Professor.
Bye-bye.
I have a question about the midterms.
Yes.
So you said you would be posting the solutions to midterms 1 and 2 like later on.
Yes. Would
it be?
Go ahead.
Would it be just the written questions, the last 2, or would it be like all of the multiple choice
all
and
of
the written?
Choice, all of everything.
Oh, okay. Thank you.
Thank you. Of course. Bye-bye.